With Osamu Iyama from Nagoya, who will speak on preprojective algebras and Calabi-Yau algebra.
Thank you very much. I'd like to thank the organizers for inviting me to this conference and giving me an opportunity to give a lecture here. So, yes, as the title shows, I will explain preprojective algebra and its higher analog, which we call higher preprojective algebra, and some of Calabi-Yau algebra aspects of higher preprojective algebra. And yes, so beginning of my talk, I think not all people know what is preprojective algebra. So I will start with some classical results about classical preprojective algebra. Okay. So maybe some of them already know, then I'm sorry. Yeah. Start with elementary things. Okay. So preprojective algebra. Preprojective algebra was introduced by Herschend and Oppermann in quiver representations theory, and also studied by many people. And recently, well, not so recently, they are applied also to study crystal basis of quantum group by Kashiwara and Lustig. And also recently, guys like Schreier applied preprojective algebra effectively to categorify cluster algebra of forming Zervinsky. So there are many aspects about preprojective algebra, but I will concentrate on rather classical and elementary subject in this talk. So yes, so throughout my talk, I will fix some field, basic field, okay? And for just by simplicity, I assume this is algebraically closed. Yeah. But most of the statement I will mention don't need this algebraically closed property. Yeah, just this is for simplicity. And yes, I start with a quiver Q. And quiver is just oriented graph. So it consists of the set of vertices and also set of arrows. Yes. For example, maybe just I give one typical infinite family, most important infinite family of quiver. It is so-called type AN. It consists of n vertices with arrows in just a line. Yes. So this is most classical example. And if once we have a quiver with a base field, then one can define an associative algebra. By the way, when I said quiver, then I always assume this is a finite quiver. So there are only finitely many vertices, and also there are only finitely many vertices. In this case, one can associate an associative algebra with an identity called path algebra. And we denote this path algebra as a KQ. And this algebra as a K vector space. So this is an associative K algebra, and as a K vector space, they have a basis consisting of passes on Q. Yes. So for example, I use this algebra as an example. In this case, there are n times n plus 1 over 2 passes, starting at I, and go to right and right, and stop at J, and I and J are all pair of integers between 1 to n, such that I is not great smaller than or equal to J. Yeah, so they are all paths, so they give us a basis of path algebra. And let me write down this algebra, this path as Pij. Yes. Then how to define, this is, so we consider K linear combination of those passes. So to get the algebra structure, what is missing is to define multiplication. And the multiplication on path algebra KQ is just defined by connecting two passes. So if you have another path starting at J and ending at K, then the composition of Pij and Pjk is just Pik. Yeah.
What is it in the case I equals j?
I equals j, also we regard it as a path of length 0. Yes, every vertex is also path of length 0. And just to take a sum of all path of length 0, we have one identity element in KQ. Yeah. So this is explain algebra structure of KQ. And maybe I show you what is actually KQ in this simplest of example. Actually, in this case, KQ is isomorphic to n times n lower matrix algebra. Yes. So this is a sub-algebra of full matrix algebra of size n over k, consisting of just lower triangular matrix. And yes, in this isomorphism, the path Pij corresponded to the elementary matrix Pij. So this is just okay, maybe yeah, this is Ij, and this is this consists of Ij entry 1 and all other entry are 0. Then we have isomorphism of K algebra. So is everything makes sense? I hope.
Yeah, I think it's maybe it's upper triangular because you've got E1n.
Yes. For me, my notation is 1, 1, 2, 1, 3, 1. Yes. Oh, yes. Sorry, yeah, you are right. Yes. Yeah, by some reason I take opposite, but it should be lower triangular matrix. Yes. Yeah, thank you very much. So now let me tell you some of property of path algebra KQ. So first property, this is also important in my talk, is that the global dimension of path algebra KQ. So global dimension is just a supremum of projective dimension of KQ module. So it is just the length of projective resolution of KQ modules, and it is always upper bounded by 1. Yes. And such an algebra is called hereditary algebra. And actually, any finite dimensional K algebra which satisfies this hereditary property is multi-equivalent to some path algebra KQ for certain quiver Q. Yeah, this is also. So in this sense, thinking about hereditary algebra is same with considering path algebra of quiver. And now I assume that well Q does not have okay. I assume Q is acyclic. Yeah, assume this. So this means Q doesn't contain oriented cycle. So the path starting at ending point and the starting point are the same. I assume there are no such cycle except vertices. In this case, yes, in this case, it is easy that the K algebra KQ is a finite dimensional over field. Yes, as a vector space K. And in this case, there are representation theory of yes, KQ module is studied from 1970s. And let me give one yes important functor to study KQ modules now. So yeah, I did not buy small model KQ. This is the category of finitely generated left KQ modules. Yes. Then this category have one important functor, which is usually denoted as tau. And yes, in this hereditary setting, we can write down it as a first torsion group between K dual of KQ to and a given module. Yes. Yeah, here I denote by D. This is just a K base. No, K dual. Yes. I always denote by D the K dual. Then this total one functor gives us end functor of mod KQ, and another, yes, we also have another functor which form an adjoint pair to tau is also given by first extension group from K dual of KQ to a given module. Yeah. and these two functors, tau and tau minus, are called as Osamu Reiten translations. Yeah. Later I will abbreviate as AR, but yeah, anyway, these two functors, a joint pair is called Osamu Reiten translation. Okay. And one remarkable property of Osamu Reiten translations is the following. Actually, yeah, it gives almost equivalence between our on mode KQ. Precisely speaking, it gives us a bijection between indecomposable and non-projective KQ modules, and also the set of I will always consider up to isomorphism when I wrote this. Then another set is isomorphism classes of indecomposable and non-injective KQ modules. So both tau and tau inverse gives us mutually inverse bijection of these two sets. And this bijection can be explained also in terms of stable category, but yeah, I will this more detail. And so this means, so once you have a KQ module, then applying these two functors, we can get to more and more a lot of family of KQ modules. And in particular, starting from KQ, so this is a regular KQ module. Then, yes, applying tau to KQ is 0 by definition, but applying tau minus to KQ, we get a new indecomposable or new modules. And modules obtained in this way is, okay, yeah, just consider full subcategory of model KQ consisting of, okay, yeah, direct sum and direct sum of them. These modules are called preprojective KQ modules. Yeah. So this word preprojective is actually already put in my title of my lecture. Okay. So now just this is minimal necessary background for representation theory of quiver for my talk. Yeah, so if you have any question, don't hesitate to ask me. Okay, so now I will talk about
what do they look like for AN?
Pardon?
What do these modules look like for AN?
AN, yeah, this is yes, good question. And if you present, okay, yeah, maybe I write example, maybe complete example for the case. Let's say 1, 2, 3, 4. This quiver case. In this case, there are 4 vertices, so this means that we have 4 simple modules. So this is a simple module concentrated on vertex 4, and similarly we have 3, 2, 1. So we have these 4 simple modules, and actually this functor tau acts in this way. So usually tau is written as a dotted arrow. So simple modules form 1 tau orbit. And there is also non-simple but indecomposable modules which have forms 3, 4, 2, 3, and 1, 2. Yeah. So this is an extension of 4 by 3. So we have an inclusion map and we have a surjective map. Yeah. So this is the two-dimensional. They are two-dimensional modules, and they also form 1 tau orbit. And similarly, you have 2, 3, 4, 1, 2, 3. They also have. They are also related by tau, and there is 1 projective and injective module here. Yes, so in this case there are 10 indecomposable modules, and this is projective indecomposable projective modules, and they are indecomposable injective modules, and I didn't explain what is an arrow, but they are called irreducible morphism, and this describes the categorical structure of the category mod KQ. Yeah, mod KQ is visualized in this way. Yes.
So where are the preprojective?
Yes, in this case, actually, everything is a preprojective module in this case. And actually, this is true for Dynkin case. And to explain this, I need to explain now what is called Gabriel's theorem. Yeah, this is some beginning of quiver representation theory. And yeah, let me explain. Yeah. So, yes. So one natural question is to characterize when the path algebra KQ is representation finite. Representation finite means that there are only finitely many indecomposable KQ modules up to isomorphism. And for example, this quiver of A4 is representation finite. Actually, there are only 10 indecomposable modules shown in this picture. And Gabriel characterized this condition by the properties of Q being a Dynkin quiver. Yeah. So Dynkin quiver is a quiver of type ADE. Yes. So I think people know type A, quiver of type ADE, but I just write here quickly. So type A we already saw at the beginning. So quiver obtained by replacing each edge by one arrow. Then we have several quivers with the same underlying graph, but different orientation. So they are called quiver of type A. And similarly, quiver of type D is have underlying graph of this form. Just here is one branch, and also quiver of type E is such a quiver. Yes. And for type E, the number of vertices n is either 6 or 7 or 8. And for other quiver, the type D case, number of vertices at least 4. And the type A, n is arbitrarily positive integer. Yes. So quiver obtained by orienting this graph are precisely representation finite algebra, hereditary algebra. This is a classical result by Gabriel. And he also shows that indecomposable KQ modules are in bijection with positive roots in corresponding root system. This is also part of his result. Yes. And so this means that, yes, depending on if Q is Dynkin or not, the representation theoretic behavior of KQ is completely different. Yeah. Dynkin case, it is only finitely many indecomposable. Otherwise, there are always infinitely many indecomposable modules. And actually, here there are some questions. So in this case, in this type A4 case, all modules are preprojective because they are obtained by applying tau inverse repeatedly to those 4 projective modules. Actually, this is also true for any Dynkin quiver. So I denote by P the category of preprojective KQ modules. Then this Dynkin case, P coincides with 4 module category of KQ module. Yeah, this is also so from starting from projective and applying tau this functor repeatedly, one can get any module. Yeah, so this is special for Dynkin case. So now let me go to let me explain preprojective algebra. And yes, preprojective algebra is in a word to give an algebra structure for this category in a certain sense. And but this is yes.
That's one question. I mean, maybe in your definition, do you want to replace KQ by the set of all projections?
Yes, KQ is a direct sum of all indecomposable projective module. Yeah. There is a Krull-Schmidt theorem, so any indecomposable projective module appear in KQ as a direct sum.
Add means
Add means yes, take a direct sum and a direct sum. Yes, I'm sorry. Yeah, you are not used to this convention. Okay, so now it's time to explain preprojective algebra. So yes, to give a simple definition of preprojective algebra, I need to introduce the double quiver of Q. Double of Q. Do I have some example? Yes, here I have one example. So if I have this quiver of type A4, then Q bar is obtained by adding opposite arrow for each arrow in Q. Yes, so there are 3 arrows, A, B, C. Then we add 3 opposite arrows, A star, B star, and C star. So this is a double quiver of Q. Then the preprojective algebra of Q. Okay, yeah, pi or more precisely writing, this is pi of KQ. This is defined as a quotient. Okay, first of all, we consider the path algebra of double quiver Q bar. Then factor out by an ideal generated by one element, which is a sum of commutators. A star minus A star A. Yes. And here A is runs over all arrow in original quiver Q1. Yes. So yes. So this is the definition of preprojective algebra, originally introduced by Herschend and Oppermann by slightly wrong sign, but later Ringel or Berger-Lenzing fixed and gave correct definition of preprojective.
I have a question. Do you have a notion of adding an arrow to a node?
You mean group?
Yeah.
Something like this?
Yeah.
Well, yeah, it is possible, but it's not. It doesn't appear in preprojective algebra context.
Then you would get those relations.
Oh yes. Yeah. If we have an arrow, just sometimes we consider such a quiver. Yeah, this is not the Dynkin, but in this case, to get the double quiver, we add another group to this matrix. Yeah. So this is also double quiver.
Infinite dimension.
Pardon?
Infinite
Yeah,
dimension.
well, infinite dimension. Usually, KQ is infinite dimension, and the pi is, mostly pi is also infinite dimension.
Another question is, what do you do when you have a vertex of valence 3
Valence is 3.
in D and E?
Well, yes, like this case. Yeah, yes, this case, I just give one example. So if we consider this type of quiver type D4, then double quiver is just like this.
And what is the convention for the minus sign?
This is always we need to take a minus. Yeah. So for example, in this case, actually this relation. So this is generated by one element, but actually this relation can be split for each vertices. So for example, if we multiply the vertex, same vertex from both right and left, then we get a new relation contained in this ideal. For example, in this case, multiply the vertex 1 to this, then what we get is A star A. This is also 0 by this relation, or precisely speaking, minus. Yeah. And yes, is this enough?
No, what happens at the valence 3?
Oh yes,
The
valence
other side.
3 case. Yes, actually in this case, A star, and this is a cycle of length star, and also B star. This is another one. Then minus C star C. This is a relation corresponding to this matrix.
Okay, so the sign is
Necessary. Yeah. But as far as we deal with tree quiver, then this sign doesn't matter. If we consider non-tree quiver, then that sign becomes matter. Yeah. Anyway, it's a bit technical point. So now let me give one
That's another question.
Yes, yes.
Is there a conceptual definition of the preprojective algebra?
Yes, probably what I'm writing now is a conceptual definition. Let me write it down now. So actually, yes, we have a, okay, this preprojective algebra pi has a z graded. Yes, pi have a structure of z graded algebra, and it is defined by as follows. So degree 0 part of arrow in original Q have degree 0, and the degree of opposite arrow adding later have degree 1. Yes. Then this relation is homogeneous of the degree 1. So this gives us z-graded algebra structure on pi. And using this algebra structure, we can also we have an isomorphism between pi and the following algebra constructed from KQ, path algebra. Yes, let me explain step by step. So first, we consider the first extension group from dual of KQ to the KQ. So we take extension group from injective cogenerator to projective generator. Then this extension space has a KQ bimodule structure because here both are KQ bimodule. So taking extension still have a structure of KQ bimodule. Then then consider the tensor algebra of this bimodule over KQ. So T means tensor algebra. Yes. Then actually this is isomorphic to our preprojective algebra pi. And this definition is much more flexible and have a possibility to generalize to higher dimensional case. And let me explain some of the property of this graded structure. So by our definition of this grading, the degree 0 part of pi is just consists of original quiver Q. So this means degree 0 part is nothing but original path algebra KQ. So this is the first property. And then, we can, so KQ is a sub-algebra and also factor algebra of preprojective algebra. So we can regard pi as a KQ module. Then we have the following decomposition as a KQ module. So this pi is, of course, graded algebra. So it has such structure. It is direct sum of degree I part for non-negative integer I. Then degree I part is isomorphic as a KQ module to tau minus I of KQ. KQ module KQ. Yes. So this is an isomorphism as a KQ module. Degree 0 part is path algebra and the degree I part is. So this is nothing but what we call the preprojective KQ module. Yes. So this is what I told you before. So preprojective algebra is nothing but to give algebra structure on this category of preprojective KQ module. And this is why we call pi as a KQ module. No, preprojective algebra. Because it is sum of preprojective modules. So now let me give some of more ring theoretic or homological property of preprojective algebra pi. And yes, as this corresponding connection between pi and the representation theory of KQ explains. Somehow the structure of pi also strongly depends on if feather Q is Dynkin or not.
So, how do you interpret the symbol tau minus I? I mean, somehow I thought that was the ith iteration of the tau minus functor, but there you said
tau minus is just the opposite direction.
Yes. So what is it? Is it the inverse of tau to the I or what?
yes, tau, for example, tau of 3 is 4, therefore tau minus of 4 is 3. Yeah, so this is just a partial converse in the
So
sense
tau is
that
an equivalence? You can invert tau?
yes, tau and tau minus are almost equivalent if we remove projective from here and injective from here.
Yeah.
Yes. So precisely speaking, we have a so-called stable category obtained by factoring out projective and factoring out injective. Then this becomes isomorphic. Yeah, they become equivalence.
And then here you claim that taking iterative inverses is the same as tendering.
Yes, yeah, exactly. So yeah, so this statement means yes, exactly, yes. Preprojective modules are nothing but iterated tensor product of this bimodule. Yeah, and this is explained by looking at this form of tau minus. Yes, tau minus is an extension group from injective, and also we can write down this functor as a tensor functor with this bimodule. Yeah, okay, I omit this, so I denote this by E. Then tau minus is nothing but taking a tensor product with this bimodule E. Yeah, so this explains, yeah, fine. We have such an isomorphism. Okay. So now, yes, it's time to explain some. Yeah, I was planning to talk about the trichotomy, but yeah, when I prepare my lecture, I noticed yeah, the time will not be enough. So I talk about only Dynkin and non-Dynkin. Yeah. Actually, yeah, for non-Dynkin also divided into extended Dynkin and other type, and the structure of pi is quite different, but now, yeah, I skip it. So Dynkin case, yes, first of all, how big pi is. And it is explained more or less by Globaldimension theorem and this isomorphism. Actually, there are only finitely many KQ modules. So this somehow explains that the pi is a finite dimensional K algebra. So this is somehow a consequence of classical Globaldimension theorem. And for non-Dynkin case, pi is always infinite dimensional. Yeah. And moreover, let's talk about the more homological property of pi. Actually, yes, Dynkin case, pi is a Frobenius algebra. Yes, in the sense that pi is isomorphic to its K dual as a one-sided module, or left module, or equivalent to right module. Yes. So classical preprojective algebra is Frobenius, and yeah, actually they have a very nice periodicity property, which will be discussed in some of lecture today. And I just mentioned another form of another property, namely, yes, for each Frobenius algebra, one can associate a triangulated category called stable category. I'm sorry, I omit the definition, but yeah, important point is Frobenius algebra associates a nice triangulated category. And this triangulated category is actually so-called two Calabi-Yau triangulated category. And yeah, this means that the cell functor in the sense of Bondar and yeah, Reiten Vandenberg, yeah, the suspension functor by 2, shift by 2 gives a cell functor. Yeah. So this preprojective, so stable category have such a nice property. And yes, let me also explain non-Dynkin case. Actually, non-Dynkin case also pi satisfy two Calabi-Yau property. And actually, this non-Dynkin case, two Calabi-Yau property is somehow much nicer in some sense, that much naive in some sense, that the bounded derived category of finite dimensional pi module, this is up to Calabi-Yau triangulated category. And actually, in this case, pi is also in Ginzburg's sense, pi is a two Calabi-Yau algebra from in the language of bimodule resolution. Yeah. So yes, so this is what I prepare for explanation for classical preprojective and path algebra. And from now on, I will talk about higher preprojective algebra.
Are you going to tell us what the Calabi-Yau thing means?
Yes, Calabi-Yau means, okay, so we have so this is a triangulated category. Okay, yeah, in your word, the property is same with derived category of Calabi-Yau variety. So precisely, if I write a precise definition, I need to have the following functorial isomorphism. So T is this stable category, and consider the morphism space from X to Y, and also consider the morphism space from Y to, okay, so assume we have auto functor S of T, then, yeah, we call S is a cell functor if these two morphism space are naturally dual each other. Yes. So D is just K dual, and X and Y are any object in triangulated category T. And yeah, so this isomorphism is a functorial both with respect to X and Y. Yes. So this is the definition of a cell functor, and we call T D Calabi-Yau for integer D if S cell functor is given by shift by D. Yeah. So in this case, we call T is D Calabi-Yau. So this is nothing but the property of derived category of coherent sheaves of on D Calabi-Yau variety.
What's a shift by D?
Yes, S is a shift by D.
What does that mean?
Oh yes, so each triangulated category have a suspension functor, and so suspension functor, yeah, if you write suspension functor by sigma, then this means this power of sigma. Make sense? Is it okay? Yeah, so now, yeah, I have 20 minutes more, so I can talk about some of our results about higher preprojective algebra. Yeah. So I don't want to spend so much time for other things. Yes, so yes, I decided to start with the definition of higher preprojective algebra. Yes. So I'm planning to give a definition of what is a higher preprojective algebra and their basic properties, and then give some example which we know. And yes, probably I will skip. I need to skip some of abstract part to give more example. So the idea is very simple. Yes. So before we start with the path algebra KQ, then we have a associated preprojective algebra. And path algebra KQ are precisely algebra of global dimension 1. So now we consider instead of hereditary algebra, just more general finite dimensional K algebra of global dimension at most D. And from now on, we fix a positive integer D. Yes. So start with such a setting. Yes. So in this case, yes, so higher preprojective algebra in this setting was introduced by Keller in the setting of differential graded category as so-called Calabi-Yau completion, but it is a differential graded algebra or category even more. So yes, today what I will concentrate is not a differential graded algebra. just an algebra version of preprojective algebra, and it was studied in my joint work with Stefan Oppermann. Yes. So the definition is very simple. So the preprojective algebra associated with lambda, which is denoted by d plus 1 lambda, or if this is too long, then I will also write pi. This is just the tensor algebra of lam over lambda of the following lambda bimodule. Yes, it is completely parallel to classical hereditary case. So we consider the highest extension group from injective cogenerator of lambda to projective generator of lambda. So this is the lambda bimodule structure as before, so we can consider its tensor algebra. Yeah. So this is the definition. Yes, very simple. And actually, yes, this also has some meaning from a viewpoint of Ausland Reiten translations, or more precisely speaking, some analog of AR translation called the higher Ausland Reiten translation. It is actually my motivation to study higher preprojective algebra. Yeah, it was motivated by higher dimensional analog of Ausland Reiten theory, but I think I don't have time to talk much about it, so I will concentrate on property of this higher preprojective algebra. And actually, yes, this preprojective algebra, usually the homological behavior of pi is not as nice as classical hereditary case. And to have a nice, for example, Calabi-Yau property of pi, we need to assume some condition called lambda to be d-hereditary. Yeah. And this d-hereditary property is defined by using cell functor or Nakayama functor of derived category of lambda. So I will not define what is d-hereditary, but the important point is d-hereditary algebra consists of two disjoint classes. One is called d-representation finite. This is actually, I will discuss d-representation finite algebra in the rest of my talk. Yeah. And also, d-hereditary consists of another part called d-representation infinite. Yes, and actually, this is also very nice class of algebra, which is corresponds to, so hereditary case. The case d equal 1, the representation finite is Dynkin case, and the representation infinite is a non-Dynkin case for d equal 1. But yes, from now on, I will discuss about the representation finite algebra. And actually, okay. And actually, yes, so I need to define what is the representation finite. This is defined by the existence of, I abbreviate the representation finite as DRF. This is defined by existence of a nice module in the representation of lambda, and such a module M is called the cluster tilting module. So I now write the definition of the cluster tilting module. So this is defined by the following equality. So first of all, we consider additive closure of n, direct sum of direct summands of n. Yes. Then this category coincides with all lambda module such that there is no extension group between 1 to d minus 1. Yes. There are no middle extension group except d minus 1. No middle extension, middle extension group from 1 to d minus 1. Such a module X must belong to already M. And also similar equality holds. Okay, I'm sorry, I can't write everything here. So same equality for the condition, just reverse the position of x and m. So this category also coincides with m. Yes. So the module m to be d cluster tilting. This is defined by the coincidence of these three subcategories of modulo lambda. Yes. And in this case, in this case, I just give one property of the representation finite algebra. Yes, actually, in this case, the projective algebra consists of lambda modules called the preprojective. Yeah. Let me explain this. So in this case, we need to consider at least one of the functor tau minus d. This is this extension group from d lambda to a given module. So this is end functor of modulo lambda. We also have another functor given by tau, but I omit. Then one of the result with Oppermann, my joint work with Oppermann is the following, namely, in this case, so assume lambda is the representation finite algebra and with the cluster tilting lambda module m. Yes. Then actually preprojective algebra is okay. Actually, in this case, preprojective algebra gives us the cluster tilting module. Yes. So in this case, yes, pi is the cluster tilting lambda module. And in this case, moreover, this pi regarded as a lambda module is a unique basic d cluster tilting lambda. Yeah. So this shows a connection between cluster tilting module and preprojective, higher preprojective algebra. And as in the case of classical preprojective algebra, we also have the following property of preprojective algebra. Namely, if lambda is the representation finite, then the preprojective algebra is still finite dimensional as a vector space over K. And moreover, pi is again a Frobenius K algebra. So the K dual of pi is isomorphic to itself. So we have a pi module. So, and moreover, yes, so we mentioned this and this and this. Then, in this case, we also have a certain Calabi-Yau property in the stable category of pi. Namely, in this case, this is a d plus 1 Calabi-Yau triangulated category. Yeah. Yes. And actually, this pi also satisfies certain twisted periodic property of resolution of simple module. So in this case, pi is also almost the Calabi-Yau. I think people call it almost Calabi-Yau in this context. Yeah. So higher preprojective algebra satisfies quite a parallel property to the classical one. And in the last 10 minutes, I will give some example of the representation of finite algebra and its higher preprojective algebra. So if you have any questions so far, please, this is a good time to ask me. I hope, yes. I don't omit so many things.
The theorem you write is only the implication is one way. Is the finite dimensionality of pi characterized?
Okay, you want this direction. So far, I don't have a counterexample. Yeah. And there's also work on Amiotand Oppermann. They discuss some kind of converse, if I remember correctly. Yeah, but not. Yeah, not. I don't think it is known. Yeah. Okay. Yeah. So let me give one series of examples. Actually, this is one of our starting point of studying the representation of finite algebra. So yeah, this algebra, this family of algebra, we call type A example, and we fix some positive integer d and s, and start with quiver Q with the following set of vertices. So the vertices of V is a d plus 1 tuple of non-negative integers, V0 to Vd. And we assume that sum of these Vi is equal to S. Yeah. So this is, this consists of only finitely many vertices. Yes. And we also consider arrows on this one here. And arrows have d plus 1 direction. And arrow in direction I from V have a target V plus alpha I. Yes. And I is shows direction from 0 to d. And what is alpha I? Alpha I plays somehow the role of simple roots in classical setting, namely, it is a vector with I minus entry minus 1 and I entry 1 and everything is 0. Yes. And because we consider this index from 0 to d as cyclic index, so if I equal 0, then this means last entry is minus 1 and first entry is 0. Yeah. So we consider such a vector alpha I. Then, maybe it's good to give one simple example: d equal to and s equal to. Yes, in this case, yes. So 0, 0, 2, 1, 0, 1, 2, 0, 0. So this is arrow in direction 1, and also 1, 1, 0, 0, 2, 0. So this is arrow in direction 2, and also yes, 0, 1, 1 here. So this is the direction of arrow. Okay, sorry, I'm sorry. This is the direction of 0. This is the direction 1, and this is direction 2, and we have also 3 more arrows here. Yes. So so this is small case, and using such a quiver, we define a new algebra grammar in the following way. So first of all, we consider path algebra of Q, then divide by the ideal generated by the following element, and yes, relation is okay. Maybe because I don't have only 5 minutes, I explain in this simple example. So basically, relations are always equality between paths of length 2. So for example, here we have a path of length 2, yes, in direction 0 and 1. Then this path of length 2 is equal to another path of length 2 in reverse order. So this is the first direction 0 to 1. Then we also consider direction 1 to direction 0. Yes. Then path of length 2 are equal. Yes. Basically, relation of this algebra is given in such a form. I to j is equal to j to I. Okay, direction ij is equal to direction ji. And sometimes it appears also in boundary like this. Yes, so this is the direction 0, then direction 1. Then we cannot go outside. So in this case, this path of length 2 is regarded as 0. Yeah. So at the boundary, we have 0 relation, and in an inner point, we have such commutative commuting relation. So this is a definition of gamma. And in this case, actually, this gamma is actually isomorphic to a preprojective algebra of several different d-representation finite algebra. Let me explain what is d-representation finite algebra associated with this. So to explain this, we need to take a set of arrows in our quiver Q. And this set is called a cut if the following condition is satisfied. Yeah, roughly speaking, this is a kind of a perfect matching, but yeah, I should explain precise meaning. Namely, for any cycle of length d plus 1. Yes, so in this case, there are 4 small triangles. So consider those 4 small triangles in that case. Then any of such such cycle contains precisely 1 arrow which belongs to our choice of arrow C. Yeah. So this is a condition of cut. And then yes, in this small example, we have yes, I think if we have yeah, okay, let me just give one example. So we choose this arrow, and this arrow, and this arrow. So all arrow in direction 2. Yes, then this is easily to be checked that this forms a cut. And actually, one of the statement we showed in Oppermann is that defining lambda c as a quotient of gamma modulo the ideal generated by some choice of cut. Then this algebra is d representation finite, and moreover its preprojective algebra lambda preprojective of lambda c is isomorphic to this algebra gamma. Yeah. So this is so yeah. In this case, there are quite a huge number of choice of cuts, but both of them gives us the same preprojective algebra. And yeah, one can regard this fact as an analog of in classical quiver representation theory. There is a so-called Bernstein-Gelfand-Ponomarev reflection functor, and this isomorphism can be regarded as a certain higher dimensional analog of it. Yeah, and yes, I think yeah. I prepare also several other examples, but if you are interested in, just ask me later. And yeah, it is time to stop my lecture. So thank you very much.
So I was wondering what are sort of natural sources, I guess you gave one here, of algebras which are finite dimensional and of finite global dimension.
What is the source of algebra of finite global dimension? This is your question?
Yes, finite dimensional and finite global.
Finite dimensional and also finite global dimension, yes. Yeah, actually, to get to, yes, maybe I should first tell you about another classical Gabriel's theorem. Namely, yes, so here we need an assumption I use sometimes that K is algebraically closed. In this case, any finite dimensional K algebra is up to Morita equivalence. It is quotient of past algebra by certain ideal. Yeah. Okay, is this what you asked? And so this means as far as you have a quiver and you have a sufficiently large ideal, then taking a factor, you have a finite dimensional algebra. And moreover, if you want algebra of a finite global dimension, then easiest way is the following, namely start from quiver Q, which is acyclic, in the sense that there are no oriented cycle in Q. In this case, KQ is always finite dimensional, and any quotient of KQ modulo I has finite global dimension. Actually, global dimension is upper bounded by the maximum length of path in Q. So, yeah, this is the most general way to give such an algebra. Yeah. But yes, one of construction I was planning to talk is to take a tensor product of two nice algebra. Yeah. If you have two finite dimensional algebra of finite global dimension, then taking a tensor product, then it also have finite global dimension. And actually, the representation finiteness is also preserved by tensor product under certain reasonable assumption. Yeah. So there are several construction.
More questions? No, I think Professor Iyama again.